I want you to picture a factory. It's this state-of-the-art facility, gleaming white floors, robotic arms whirring all over the place. The best engineers in the world are walking around in lab coats. They're building the most advanced cars the world has ever seen. The engines are perfect. The aerodynamics are, just flawless. But here's the catch. At the end of the assembly line, instead of driving these cars out to a dealership to be sold, they just park
Well,
them.
worse, they pushed him off a cliff.
Right. They just push them into a ravine, or they shove them into some dark warehouse to just sit and rust. 80% of them. Maybe even up to 100% of them.
It sounds like, I don't know, a failed state economy or maybe some kind of bizarre money laundering scheme.
It does. But what if I told you that this factory, it's actually a pretty accurate metaphor for the current state of artificial intelligence in the corporate world?
I think I know where you're going with this.
Because I was reading through the source material for this deep dive, specifically the AI Playbook by Eric Siegel. And I hit a statistic that, honestly, it made me stop and reread it 3 times.
The deployment statistic.
Yes. A majority of data scientists report that 80 to 100% of their models never deploy. They never see the light of day.
They never make a decision.
Never make a single dollar. They're just expensive digital paperweights.
It's a staggering number. And, we're not talking about hobbyists tinkering in a basement here. We're talking about Fortune 500 companies. We're talking about banks, insurance giants, massive logistics firms.
The big players.
The biggest. And they are spending millions, arguably billions collectively, on what is effectively a science fair project that nobody ever comes to judge.
That is the core tension we really need to unpack today.
Yeah.
We live in this world that is, it's absolutely obsessed with AI. It's writing poetry. It's generating videos of, astronauts riding horses on the moon. It's supposedly coming for everyone's job. But when you strip away all that hype and you look at the actual ledger, the businesses trying to use machine learning to do serious, profitable work, it is, to put it mildly, a disaster zone.
It's a quiet crisis, though. That's the thing. The technology, fundamentally, it works. The math is sound. The algorithms are brilliant. But the implementation, it's just broken.
So today we're going to try and fix it. Or, well, maybe not fix it ourselves, but we're going to look at Eric Siegel's 6-step practice that he designed to fix it. He calls it BizML. And the whole mission here is to build a bridge between the suits, the business leaders, and the hoodies, the data scientists.
Because right now, they are speaking completely different languages. It's like one is speaking Klingon and the other is speaking, ancient Greek.
And looking at the notes, this isn't just another how-to guide full of code snippets. It's really an analysis of human behavior. Siegel identifies these 2 massive blockers that keep all those models from launching. He calls them the can'ts and the won'ts.
The can'ts and the won'ts.
The can'ts seem pretty straightforward. That's the technical stuff, right? Like, we can't do this because our servers are from 1998, or we just don't have the right data.
Precisely. That's the infrastructure hurdle. It's a real problem, don't get me wrong.
Yeah.
But Siegel argues it's actually the smaller problem, the meaningful problem, the one that is killing that 80 to 100% of projects, is the won'ts.
The won'ts. Okay, so what's that?
This is the business leader in the corner office looking at the presentation and saying, I won't approve this. Not because the model doesn't work mathematically, but because it requires a fundamental change in operations. And this brings up what Siegel calls the innovator's paradox.
Okay.
The more radical the technology and machine learning is about as radical as it gets for a traditional business, the more it disrupts the status quo. And the more you disrupt that status quo, the harder it is to sell the idea to the very people who are currently in charge of running that show.
It's the classic difference between selling someone a faster horse and selling them a car. If you sell them a car, you also have to convince them to build roads and gas stations and traffic lights and learn a whole new set of rules for driving.
And most executives, if they're being really honest with themselves, deep down, they just want the faster horse. They want the AI to just magically sprinkle some dust on their existing processes and fix things without them having to actually change how they run their department.
So today, we're going to be moving away from the gee-whiz sci-fi stuff. We're getting into the, let's be honest, the unglamorous, gritty, but frankly, incredibly profitable world of logistics and operations and churn prediction.
We're going to see why boring is actually where all the money is.
I would argue boring is just another word for reliable. And that's really what businesses are aiming for, right? Reliability.
That's the goal.
Okay, so let's start with a tale of 2 projects. We have a failure and we have a success. And what I love about this is that the failure actually comes from the author himself, Eric Siegel. He's not just, critiquing others from an ivory tower. He's confessing his own sins here.
It's a very brave admission, I think. The story goes all the way back to 2003. Siegel had just launched his consultancy in San Francisco. It was, still the wild west of the dot-com era. And he lands this massive client, gay.com.
Which, for context, for anyone who might not know or remember, was a huge social platform back then, a real pioneer.
Oh, massive. Millions of users, a huge online community. But they had a leak in the bucket, a big one. They had a massive turnover problem, what we call churn in the business world.
Churn is the silent killer of so many subscription businesses.
It is. It's absolutely brutal. You spend all this money to get a customer to sign up, marketing, ads, special promos, and then they just leave after a month or two. You never make your acquisition costs back. So gay.com brought Siegel in with a very clear mission: stop the bleeding. Use this newfangled thing called machine learning to predict who is going to leave so we can step in and save them.
And the financial stakes here, they weren't small, were they?
No, not at all. They ran the numbers. If they could retain just 5% of the defectors, just 1 out of every 20 people who are about to quit, it would yield about $862,000 in annual profit.
Wow. Nearly $1 million just for saving a tiny fraction of customers. That seems like a complete slam dunk incentive.
You'd think so.
So Siegel goes into his lab, he crunches the numbers. What does he build?
He builds something called a decision tree. Now, we should probably pause and explain what that actually is, because it sounds a bit like gardening, but it's really pure logic.
I always think of it like the game 20 questions.
That is the perfect analogy. It's exactly like that. Imagine you're playing 20 questions. You start with a broad question. Is it an animal? If the answer is yes, you go down one branch. Does it bark? If yes, you go down another. Is it a golden retriever? The computer does this exact same thing, but instead of animals, it's looking at user behavior.
So it's asking questions like, did this user log in the last 24 hours? No. Okay. Did they try to start a chat yesterday? Yes.
Exactly. And it does this thousands and thousands of times a second across all the data to find the hidden patterns, the little combinations of behaviors that strongly correlate with quitting.
And did he find one?
Oh, he found a great one. Siegel's model spit out a very specific rule. It was incredibly precise, it said. If a user has tried to initiate a chat and they signed up less than 238 days ago and they had a failed login attempt recently, then there is a 43% chance they are going to cancel their subscription.
Less than 238 days? That is such a machine number. A human marketing manager would say less than 6 months or less than a year. They'd round it off.
Humans round numbers up. We like neat, clean numbers. Machines don't care. The machine crunched all the data and found that the statistical tipping point was not day 230, not day 240, but exactly day 238. That's the kind of insight you just can't get from a spreadsheet. That's the gold.
So he has the smoking gun. He knows who's about to leave. He puts this all in a slide deck. He walks into the boardroom with the executives.
Yeah.
He presents the math. Here are the people. Here's how we know they're leaving. Here is your $1 million waiting for you.
And the executives looked at it, they nodded, and they said, wow, that is fascinating.
And then?
And then they did absolutely nothing.
Nothing.
Nothing. The model was never deployed. It was never used to make a single offer. The project died right there in that room.
But why? I don't get it. You are literally leaving $1 million on the table. It's just sitting there.
Because to use the model, they had to change the business. They couldn't just know who was leaving. They had to do something about it.
Right, the action part.
And that meant authorizing a special discount program, which required getting approval from the finance department. It meant changing the website code to pop up an offer to these specific users, which required getting on the schedule for the already overworked engineering team. Yeah. It meant training the customer service reps on what to say when these people called.
So Siegel sold them the math.
He sold them the math, but he completely failed to sell them the operational change. He showed them the diagnosis, but not the treatment plan. And the treatment plan looked like a lot of work and a lot of interdepartmental meetings.
It's the ML paradox in perfect action. The prediction was brilliant, but the project was a total failure because the organization wasn't ready or willing to act on it.
It was a beautiful science experiment, and businesses, at the end of the day, they don't pay for science experiments, they pay for results.
Okay, that's the failure. A bit of a downer.
Yeah.
Let's cleanse the palate. Let's look at a massive success. And this one involves what is arguably the most complex logistical ballet on Earth, UPS.
The big brown trucks. This story is the gold standard of operational ML. And the hero of this story is a guy named Jack Levis. Now, I want you to pay very close attention to his title. He wasn't the chief AI officer or the head of innovation.
What was he?
He was the senior director of process management.
Wow, that sounds like the most bureaucratic, paper-pushing title you could possibly imagine.
It does, doesn't it? But that's the key. He wasn't a tech guy. He was an operations guy. He lived and breathed the actual physical mechanics of the business, and he was trying to solve something he called the delivery paradox.
The delivery paradox. Let's unpack that, because I think most of us just, a package shows up on our porch, and we don't think for a second about how it actually got there.
The paradox is a fundamental timing problem. To load a delivery truck efficiently so the driver isn't digging through a mountain of boxes for 10 minutes to find the one for our 123 Main Street, you need to know exactly what is going on that truck before you start loading. You need the full inventory, and you need to load it in reverse order of delivery.
Last package on is the first package off. Makes sense.
And here's the paradox. Packages are arriving at the UPS facility all night long. Planes from across the country land at 4 a.m. Feeder trucks from other hubs arrive at 6 a.m. You literally do not know the full final list of deliveries until right before the trucks have to leave for the day.
So you have this impossible choice. You either wait for every last package to arrive,
Right.
which means your trucks leave late and miss their delivery windows, or you start loading blindly and your trucks are a chaotic mess and your drivers waste hours searching for packages.
Exactly. It's a classic catch-22 of logistics. And Jack's idea was revolutionary. He said, what if we don't wait? What if we use machine learning to predict what packages are coming tomorrow before they even arrive at our facility?
So he's essentially creating a ghost inventory, predicting the future manifest based on historical data.
That's it. It was called package flow technology, or PFT. But here is the absolute genius move, and this is what contrasts so directly with the gay.com story. Jack didn't pitch AI. He didn't walk into the boardroom talking about decision trees or neural networks or gradient boosting.
He didn't show them the math.
He didn't show them the math. He showed them the solution. He pitched it as operations research. He went to the executives and said, I have an idea that can solve our truck loading problem and make our routes more efficient. He spoke their language: operations, efficiency, cost savings.
And there's this fantastic story in the book about how he finally got the C-suite on board, the ride-along. I love this because it really visualizes the difference between telling someone something and showing them.
Yes. So Jack is trying to convince this one particular executive, guy named Chuck. And Chuck is skeptical. He's an old-school logistics guy. He trusts his gut. So Jack does something brilliant. He puts Chuck in the passenger seat of a delivery truck that is using this new PFT system for its route.
They're out in the wild. No more PowerPoint.
Exactly. They are on the road. Now, the system is guiding the route on a little screen. And at one point, the system tells the driver to drive right past 3 houses that have deliveries. Just skip them.
Which has to go against every single instinct a delivery driver has. You see the house, you have the box in the truck, you stop and deliver it.
It feels completely wrong. It feels inefficient. It feels like a mistake. Chuck is probably sitting there thinking, see, I knew this computer thing was a dumb idea. But the system knew something the humans didn't.
What did it know?
It knew that based on the time commitments for other premium, high-priority packages further down the route packages that absolutely had to be there by 10:30 a.m., and based on real-time traffic patterns, it was actually mathematically faster to skip these 3 non-urgent stops now and catch them on the way back at the end of the loop.
That is some deep, counterintuitive logic. My brain would never do that.
Of course not. A human can't process that many variables at once. But Chuck sat there. He watched them skip the stops. He probably got nervous, tapping his foot. But then he saw them hit all the premium deadlines perfectly, and then he saw them circle back and finish the entire route faster than the normal human-planned route. He saw the logic physically play out on the road in front of him.
And that was the epiphany.
That was the moment. He didn't need to see the code. He didn't need to understand the algorithm. He needed to see the truck turn left when his gut told him to turn right and see that it worked.
And the impact of this.
Yeah.
When it rolled out company-wide,
it was staggering. By optimizing these routes and truckloads, they saved 185 million miles of driving per year.
185 million miles. That's what, to the sun and back?
Something like that.
That's
a mind-boggling number. And it translated to over $350 million in savings annually.
$350 million. That is the difference between a cool science project in a boardroom and a full-blown business revolution.
And that right there is the difference between Gay.com and UPS. One company focused on the model, the other focused on the operation.
So this brings us to the core of the book, the framework itself. BizML Siegel says this is the bridge.
Yeah.
But you made a distinction earlier that I want to circle back to. You said this isn't a technical framework.
No, and that's a critical distinction to make. We have plenty of technical frameworks out there. We have things like MLOps, which is all about the engineering side, how to maintain code, how to do version control for models, how to monitor them in production.
Techies.
For the techies. And we have older things like CrispDM, which is this ancient standard from like 1996 for data mining. But those are for the engineers. Those are for the people in the hoodies. BizML is for the leaders. It's a business practice. It's a way of thinking.
And Siegel's core philosophy for it is plan backwards, which on the surface sounds a bit like Stephen Covey's start with the end in mind.
It is, but it's very specifically applied to data projects. Most companies, and I mean most of them, start with the data. They do a big inventory. They look at their servers and say, wow, we have terabytes of customer logs. We have all this sales data. What can we learn from this?
That feels like the natural starting point. Here are all our ingredients. What kind of meal can we cook?
It feels natural, but in business, it's the absolute wrong direction. It leads to what they call aimless wandering. You spend 6 months exploring the data and come up with some fascinating insights that nobody knows what to do with.
Like the Gay.com project.
Exactly like the Gay.com project. Siegel says, start at the very end. Start with deployment. What single operation are we trying to improve? Do we want to fix truck loading? Okay. How exactly will we do that? We will change the routing software to accept a new input. Okay, now, and only now, what data do we need to generate that input?
It completely flips the script. It prevents that whole solution in search of a problem dynamic.
Precisely. And this requires something that Siegel calls data literacy. And I want to be really clear here because this term scares a lot of business people. This does not mean the CEO needs to learn Python.
That's a relief. I don't think my boss is going to be firing up a Jupyter notebook anytime soon.
No. Think of it like driving a car. You, the driver, you do not need to know how the fuel injection system calibrates the air-to-gas ratio. You don't need to understand the metallurgy of the transmission gears. That is for the mechanic, the specialist.
The data scientist.
Right. But you as the driver do need to know the rules of the road. You need to know that if you turn the wheel left, the car goes left. You need to know what the brake pedal does. You need to understand momentum and friction and how to navigate in traffic.
So BizML is basically driver's ed for executives.
That is the perfect metaphor. You don't need to build the engine, but you absolutely cannot be asleep at the wheel.
All right, let's get into the manual then. The BizML framework has 6 steps, but we're going to focus on the first 3 today because these are really the foundational ones. If you mess these up, doesn't matter how good your code is, the project is dead. Step 1 is value.
Value. Establishing the deployment goal. This sounds incredibly simple, maybe even a little condescendingly so, but it is where 90% of projects trip up right out of the gate. Siegel boils it all down to a simple deployment equation.
Okay.
Every single machine learning project must be defined by 2 and only 2 things. First, what is predicted, and second, what is done about it.
Prediction and action.
Prediction and action. If you cannot clearly and simply articulate what is done about it, you do not have a business project. You have a research paper.
This reminds me of the AI first trap that the book talks about. Every company wants to be AI first now because Google does it.
Right. Everybody wants to be Google.
Yeah.
But you are not Google. For Google, their core product is the search algorithm. For 99% of other companies, AI is a tool to fix a pre-existing business problem. If you put the solution, AI, before the problem, you end up with a very, very expensive toy.
Let's look at the EduPay example from the notes. This really clarified the concept for me. This was a scholarship search engine, right?
Right. So EduPay's business model was simple. They showed ads to students using their site, click here for a great student loan or check out this university, that sort of thing. The problem was their ad targeting was generic. They were basically using the old spray and pray method.
Just show the most popular ad to everyone and hope that something sticks.
Exactly. Which is wildly inefficient and costs a lot of money in missed opportunities. So they came in and they defined the value using Siegel's equation. Part 1, prediction. Will this specific user, seeing this specific ad at this specific time, click on it?
Very precise.
And then part 2, the action. We will automatically display the ad with the highest probability score for that user in that moment.
It seems so obvious when you lay it out like that.
It is obvious in retrospect, but the magic, the reason it worked was that the business leader, a woman named Melissa, had the entire deployment plan approved before a single line of code was written for the model. She knew exactly how the website's ad server would be changed to accommodate the model's output. She
Oh.
wasn't asking her team, can we predict clicks? She was asking, how will we operationalize click predictions to make more money?
She built the road before she bought the car.
Bingo. And the menu of options here is just huge. It's not just about ads. This applies everywhere.
Right. The notes mention marketing, finance, even the public sector.
It's everywhere. In marketing, it's called response modeling. Who will buy this product if we send them a catalog? In finance, it's credit scoring. Who will default on this loan? In the public sector, it's risk assessment. Which restaurant is most likely to fail a health inspection? Or which building is at the highest risk of a fire?
There's also a distinction the book makes between detection and prediction that I want to touch on, because those terms get used interchangeably all the time, but they are slightly different.
They are. It's a subtle but important difference. Prediction is usually about the future. Will this customer churn next month? It hasn't happened yet. Detection, on the other hand, is about the present, but the hidden present.
Like spotting fraud.
Exactly. Is this credit card transaction happening right now fraudulent? Or in healthcare, does this medical scan that I'm looking at right now show a tumor? The event exists in the present moment, but it's hidden from us. But functionally, for BizML, they work the same way. The machine predicts a probability, and you take an action based on that probability.
So, whether you're predicting the future or detecting the hidden present, the deployment equation still holds. What is the probability and what do we do about it?
Precisely. It's the universal starting point.
Okay, so that's step one. Value. We know what we want to do. We have our prediction and our action. Now we move to step two, target. Establishing the prediction goal. This feels like we're just refining step one. Why is this a whole separate step?
Because the devil is in the details. It is not enough to say, we're going to predict churn. That is way too vague. And vague goals lead to completely useless models. This is where you have to get painfully specific.
Let's go back to the gay.com story. If they'd done this step correctly, how would they have refined their goal?
Okay, so if they had just said predict if a customer will leave, the data scientists might have built a model that was really good at predicting people who are leaving tomorrow.
Which is way too late.
Way too late. If they're leaving tomorrow, they've probably already packed their bags and made up their mind you can't save them. Or, on the other end of the spectrum, the model might predict people on annual plans who are going to leave in 10 months.
Which is way too early. You don't want to give a discount to someone who is happily locked in for another year.
Right. You'd be giving away margin for no reason, so they needed to refine the target. A good target wouldn't be, will they leave? It would be, will a customer who is currently on a monthly or quarterly plan intentionally cancel their subscription within the next 3 months?
Every part of that sentence is doing work. Monthly or quarterly plan. Intentionally cancel within the next 3 months.
Exactly. Intentionally cancel is a key phrase there, because some people cancel passively. Their credit card on file expires. You don't need a fancy predictive model for that. You just need an automated email that says, hey, please update your credit card. You only want to target the people whose minds you can actually change.
There was another fantastic example about a bank that really highlighted this too late problem. This one actually made me laugh in a sort of tragic corporate way.
This is a classic be careful what you wish for scenario in data science. A bank wanted to predict which customers were going to close their accounts. They built a model, and it was super accurate. It found a segment of customers who had a 44% chance of leaving.
That sounds great. That's a huge signal.
It sounds great on the PowerPoint slide, but when they actually looked at the list of people the model had flagged, they realized these people had already emptied their accounts. Their checking account balance was 0.
Oh, yeah.
They had effectively already left. They just hadn't gotten around to filling out the closing paperwork yet.
So the model wasn't predicting the illness, it was predicting the funeral.
That is the perfect analogy. The insight wasn't actionable because the event had, for all intents and purposes, already happened. So they had to go back to step 2. They had to fix the target. Instead of predicting account closure, they changed the target to partial disengagement. They started looking for a steep drop in the number of transactions or a big outflow of money that wasn't the whole balance.
So that happens before they take the last dollar out.
Exactly. It's the leading indicator. If you catch them there, you still have a chance to call them, make an offer, and save the relationship.
This seems to be a recurring theme. The prediction must match the rhythm and the language of the operation itself.
It has to speak the language of the business. Remember the UPS story. Jack Levis needed to predict package deliveries. But he couldn't just predict, will a package go to the zip code? That wasn't nearly granular enough.
Because a zip code can be huge, dozens of streets, thousands of people.
Right. Knowing a package is going to the 90210 zip code doesn't help you load the truck in the right order. He needed to predict at the sequence level a specific cluster of addresses that a driver typically hits in a specific order.
Because that's how the route planning software already worked.
Exactly. The prediction had to fit perfectly into the existing slot in the software. If it didn't, the whole thing would have been useless. This is why the business folks and the tech folks have to be in the room together for this step. Siegel talks about it like a Venn diagram. Circle A is things the business wants to predict. Circle B is things the data can actually predict.
And the goal is to find the overlap.
You have to live in that little sliver of overlap. Sometimes the business wants to predict something that's basically impossible, like which specific employee will commit fraud next year. Well, if you don't have any historical data on employee fraud, or if it's an incredibly rare event, you just can't predict it directly. You have to find a proxy, a different target that works for both sides.
And this is where some of the ethical questions can come in too, right? With the target variable.
Absolutely. If your target is biased, your model will be biased. If you build a model for predictive policing and your target variable is arrest rate, and past arrest data has been influenced by racial bias, your model will just learn to replicate and amplify that bias. The choice of target is not just a technical decision, it's a deeply ethical one.
So we have value, the prediction, and the action. We have target, the super specific granular definition of what we're predicting. Now we get to step 3, performance. How do we keep score? And this is where I think the general public and, frankly, the media gets the most confused. We all hear the word accuracy, and we think we know what it means. But Siegel says accuracy is a dangerous fallacy.
The accuracy fallacy. This is the big lie of so much AI marketing and media coverage. You see these headlines all the time. New AI can predict criminality with 90% accuracy.
And that sounds terrifyingly effective. It sounds like something out of Minority Report.
It does. But let's dig into a real example. The Stanford Gaydar study that Siegel breaks down in the book. This made huge waves a few years ago. The claim was that an AI could distinguish between photos of gay and straight faces with 91% accuracy.
91%. I mean, that sounds almost perfect. Better than a human could do.
It sounds incredible, but you have to look at how the test was actually run. It was something called a pairing test.
Okay, unpack that for me. What is a pairing test?
Imagine I show the computer 2 photos side by side. I tell the computer, okay, one of these men is gay and one of these men is straight. All you have to do is tell me which one is which. It's a forced choice.
So it's basically a coin flip with a bit of extra information. The starting odds are 50-50.
Right, and the computer could do that correctly 91% of the time. But that is not how the real world works. In the real world, you don't walk around in neatly labeled pairs, you walk around in a crowd. And in a random crowd, gay men are a minority of the population. Let's say 7% for the sake of the study's statistics.
So the baseline probability isn't 50-50, it's more like 937.
Exactly. Now, if you apply that same model, the one that looks so good in the easy pairing test, to a random crowd, it completely falls apart. In order to correctly identify most of the gay men in the crowd, it would have to cast a very wide net. And because there are so many more straight men in the crowd to begin with, the model would end up wrongly labeling a massive number of straight men as gay. The number of false positives would be enormous.
So the 91% accuracy is totally meaningless in a real-world deployment context because the harm from the false positives would be catastrophic.
It's worse than meaningless, it's dangerously misleading, and accuracy fails even harder when you're dealing with really rare events. Imagine I tell you I've built a model to predict if you will win the lottery.
Okay, I'm listening very carefully.
My model is very simple. It just says no for every single person. No, you won't win. No, your neighbor won't win. No, nobody on earth will win.
Well, you'd be right, 99.9999% of the time.
Exactly. My model is 99.99999% accurate. I'm a data science genius, but my model is also 100% useless because it never identifies the one person who actually does win.
This is the base rate problem, the class imbalance problem.
Yes. If the thing you were trying to find is rare, like a customer who buys a niche product or a fraudulent transaction among millions of legitimate ones, or a lottery winner, accuracy is a terrible, terrible metric. A model that literally does nothing can still be incredibly accurate.
So if accuracy is a trap, what should we be using instead? What's the right way to keep score?
We should be using LIF.
Lift.
Yeah.
I love the analogy Siegel uses for this, the TV size analogy. It made it click for me.
This is the best way to visualize it. Imagine you're a marketing executive for HBO, and you want to predict who is most likely to subscribe. You line up everyone in your city in one long row, but you don't line them up randomly. You line them up based on the size of their television.
So you have the people with the tiny 13-inch kitchen TVs on the far left and the people with the giant 80-inch home theater systems on the far right.
Exactly. Now, let's say that generally, across the whole city, 30% of people have an HBO subscription. That's your baseline. But if you walk all the way to the far right of the line, the people with the massive TVs, and you survey just that top group, you might find that 70% of them have HBO.
Makes intuitive sense. If you invest in a big TV, you probably love movies and prestige content.
So the general rate in the population is 30%, but the rate in your big TV group is 70%. That's more than double the average rate. Your model, which is simply using TV size as the predictor, has improved your odds by a factor of roughly 2.3. That is your lift. You have a lift of 2.3.
So you aren't perfectly predicting anything. You don't know for sure that a guy with a big TV has HBO. He might not.
No, you absolutely don't. 30% of them still don't have it. But you know he is more than twice as likely to have it as the average person. And in business, targeting people who are twice as likely to buy is pure gold. This is what Siegel calls the prediction effect. You don't need a crystal ball that's 100% right. You just need to be better than guessing. You just need to beat the baseline.
This connects back to the Nate Silver example, right? The election forecaster.
Yes, it's the perfect parallel. In 2016, Silver's model gave Donald Trump about a 30% chance of winning the election. When Trump won, so many people yelled that Silver was wrong, that the data had died. But Silver was never wrong. He said there was a 30% chance. Things with a 30% chance happen. Well, they happen about 30% of the time.
It's like rolling a 10-sided die. If I say you might roll a 1, 2, or 3, and you roll a 2, I wasn't wrong.
Exactly. But in elections, we only get to run the experiment once, so it feels like a binary failure. In business, we get to run the experiment millions of times a day. If UPS predicts package flow, they do it for millions of packages. If they are right more often than they are wrong, if their model has positive lift, they save millions of dollars over the long run.
Okay, let's talk about that money shot.
Yeah.
How does lift actually translate to profit? Because lift of 3 sounds like an abstract data science term, but profit is very real.
Let's do the math. Let's take a classic response modeling case. Say you're a retailer with a customer list of 1 million people. And from past campaigns, you know that generally only 1% of people who get your catalog will actually buy something. So that's 10,000 potential buyers hidden in a haystack of 1 million people.
Okay, 1 million customers, 10,000 buyers.
Now, let's say it costs you $2 to print and mail each catalog. If you mail it to all 1 million people, the spray and pray method, you've just spent $2 million on postage and printing before you've made a single sale.
That is a massive upfront cost, a huge gamble.
It is. And if the profit from those 10,000 sales isn't more than $2 million, you might actually lose money on the whole campaign, mostly because you wasted so much postage on the 990,000 people who just threw the catalog straight into the recycling bin.
Right.
Now, let's say you build a model, and the model tells you it has found a top tier of customers where the response rate isn't 1%, it's 3%. Your model has a lift of 3 for this group. And let's say this group contains 250,000 people.
So we start mailing everyone. We only mail our top 250,000 prospects.
Correct. Your printing and postage costs are immediately slashed by 75%. You save $1.5 million right off the bat. But because that smaller group is so much richer in buyers, thanks to the lift, you still capture a huge chunk of the potential sales. You're fishing in a much more densely populated pond.
You aren't creating new customers out of thin air. You're just getting much, much more efficient at finding the ones who are probably going to buy anyway.
Exactly. And the math often works out that by spending less on marketing to the wrong people, your overall profit can multiply by 5x, 10x, even more. It's all about eliminating waste.
And in something like credit scoring, the math is even more dramatic, isn't it?
It is, because the cost of being wrong is so much higher. In marketing, if I send you a catalog and you don't buy, I lose $2. It's no big deal. In banking, if I give you a home loan and you default, I could lose hundreds of thousands of dollars.
That hurts a whole lot more than a $2 catalog.
A whole lot more. So in that world, avoiding a bad customer is actually far more valuable than finding a good one. A model that can accurately separate high-risk applicants, say a group with a 17% default rate, from low-risk applicants, a group with a 3% default rate, isn't just about making the bank more efficient. It's the difference between that bank losing $200 million in a year and making a profit of $160 million. It's existential.
So lift isn't just some vanity metric for the data scientist to put on a chart. It is the direct driver of the bottom line.
It's the only metric that matters for the business case, and that's why step 3, establish evaluation metrics, is so crucial. You have to agree before you even build the model that lift and profit are how you are going to judge success, not 99% accuracy.
Okay, we have covered a ton of ground here. We talked about the tragic failure of Gay.com and the incredible success of UPS. We defined BizML as a business practice, a driver's ed course, not a technical manual. And we've walked through the first 3 foundational steps.
Step 1, value, defining the prediction and, crucially, the action.
Step 2, target. Getting super granular and painfully specific about what behavior we're actually predicting.
And step 3, performance, ignoring the siren song of accuracy and focusing laser-like on lift and profit.
If you get those 3 right, you're doing that backward planning that makes deployment, actually possible instead of just a fantasy.
That's the foundation. Everything else is built on top of that.
It really requires a pretty fundamental mental shift, doesn't it? For management, especially.
It really does. It's the leap from what Siegel calls probabilistic thinking, which is like Nate Silver sitting on TV pondering an election outcome, to probabilistic doing. UPS isn't just thinking about probabilities. They are optimizing millions of packages every single day based on those probabilities. They are acting on the odds at massive scale.
And that requires management to let go of a little bit of control, to trust the math.
A lot of control sometimes. You have to trust the algorithm. You have to accept that the model will make mistakes sometimes. It will send a truck down a weird street. It will offer a discount to the wrong person. It won't be perfect. But if the lift is there, the aggregate result over millions of decisions will be vastly superior to human intuition alone.
It brings me all the way back to that driver's ed analogy we were talking about.
Right.
You don't need to be able to build the engine. You don't need to know how to code the algorithm. But if you don't know the rules of the road, if you don't understand value, target, and performance, you are going to crash the car.
Or, much more likely, you're just never going to take it out of the garage. It'll just sit there resting, like 80% of the models being built today.
So here's the final thought I want to leave with everyone listening. We always hear that AI is being held back by, computing power or a lack of data or data privacy laws or the sophistication of the algorithms. But based on everything we've unpacked today from the AI playbook, it feels like the real bottleneck isn't the technology at all.
The bottleneck is organizational psychology.
Exactly. The bottleneck is us. It's our resistance to change. The bottleneck is your boss refusing to alter a business process that's been in place for 20 years. The bottleneck is the marketing team wanting to stick to their gut feelings instead of the data. So the question for you isn't, is your data ready for AI? The real question is your organization ready to change?
Are you really ready to let a probability drive your truck?
That's the $1 million, or in UPS's case, the $350 million question. Until next time, keep asking what is predicted, and more importantly, what is done about it. Thanks for listening to The Deep Dive.
See you next time.